Hi, hello, and welcome to BK's Tech Stack. I am BK. Today, we are going to learn about the scaling nightmare, why N times M integration fails.
Hello everyone, I'm VK. Today we are looking at the N by M problem. Imagine you have 3 AI models and 3 tools. That creates 9 unique connections to maintain. As you add more, the complexity grows exponentially. This is a common bottleneck in enterprise AI, where developers spend more time fixing brittle integrations than building actual intelligent features.
To solve this, we introduce the Model Context Protocol, or MCP. Think of it as a universal adapter. Instead of every model learning a custom language for every tool, they all plug into one standard interface. This simplifies your architecture significantly, turning a messy web of dependencies into a clean hub-and-spoke model.
MCP relies on 3 distinct roles. The host is your AI's brain, the client acts as the connector for logistics, and the server provides the toolbox of capabilities. This separation of concerns ensures that your models remain agile while your tools remain secure and reachable, all communicating via a lightweight messaging format called JSON RPC 2.0.
Let's see how we write this in code. With the fast MCP library, we define an instance and decorate our functions with @mcp.tool. This automatically registers them as available services. Notice how clean the interface is. We don't have to handle the complex HTTP or STDI networking layers ourselves. The SDK handles that for us.
Once you've written your server code, you simply run it as a standard Python process. It will listen on the specified port. Because MCP supports multiple transports, like STDIO or HTTP with SSE, you can easily switch between running this locally for testing or deploying it as a remote service in production without changing your business logic.
You might wonder how data actually moves. The transport layer handles this. It hides the complexity of networking. Whether your model is chatting with a tool on the same laptop using STDIO or hitting a remote cloud service via HTTP, the protocol ensures the packets arrive in the right order. It's truly a universal approach to tool communication.
Every interaction in MCP follows a strict lifecycle. It starts with a handshake where the parties agree on what tools are available. They then exchange messages, like a request for data or a status notification, and finally, they close the connection. This formal structure prevents hanging connections and memory leaks, which are common in unmanaged API calls. What about function calling? Previously, you had to hard-code parameters, which is a nightmare if a field name changes from guests to adults and children. MCP wraps these calls in a structured, contextual layer. Because the protocol is model-agnostic, your tools will work seamlessly whether you are using GPT-4, Claude, or a local open-source model.
Take a look at how MCP handles the message pattern. Every request includes a method name and parameters. The result is just as clean, allowing the AI to parse the output reliably. This predictability is what allows the system to scale. You aren't guessing the shape of the data anymore. You're working with a contract. Not every call succeeds, and that's okay. MCP handles failure gracefully by including specific error codes in the response. We also use notifications for one-way events, like when an AI is performing a long-running process and just wants to let the user know it's still alive. This makes the user experience much more responsive. It is important to distinguish MCP from other protocols like Google's A2A. A2A is designed for high-scale, stateless machine-to-machine communication. MCP, however, is purpose-built for the AI agent context. It is session-oriented, which means it keeps track of the state of the conversation and the tools connected to it, which is essential for AI reasoning.
We must talk about security. Recently, a vulnerability was found where attackers could hijack AI tool calls via malicious inputs. The issue wasn't a bug in the code, but a design challenge. Trusted tools were blindly executing untrusted instructions. Always apply guardrails to ensure that your agent only interacts with tools it's permitted to use.
How do we stay safe? First, use granular permissions. Don't give an AI admin access if it just needs to read logs. Second, monitor your agent's behavior.
If it starts doing something suspicious, like trying to pull secret repository files, the monitoring layer should stop it immediately. Security is a continuous process, not a one-time configuration.
To wrap up our coding section, here's how we handle resources. By using URI-like patterns, we can fetch specific data segments on demand. The client simply calls greeting/Alice, and the server resolves this to the function. This is incredibly powerful for building AI assistants that need to pull user-specific data from various back-end systems.
You've done great today. We covered how to move from chaotic, hard-coded connections to a clean, scalable protocol. We looked at the roles of the host, client, and server, how to write your own server with Python, and how to stay secure. You now have the foundation to build much smarter, more adaptable AI systems. Any questions?
Congratulations! You just learned presentation topic. Now it's your turn to apply these skills. Drop a comment below and let me know what you're building. If this helped, smash that like button, subscribe to BK'sTechStack for more weekly tutorials, and share this with someone who needs it. Visit www.BK'sTechStack.com for free resources, exclusive tips, and our community. Next video, we're diving deeper. Don't miss it.